This week in lab, we are doing an Aldol condensation, and we're doing a crossed Aldol. We are going to take an aldehyde, and the aldehyde that we are using is benzaldehyde. And we're going to react this with a ketone. And the ketone that we are using is acetone. So this is a crossed aldol between an aldehyde and a ketone. In lecture we've talked about that. That is called a Claisen-Schmidt reaction. If you're doing between an aldehyde and a ketone, a cross between those. We're going to be using sodium hydroxide as the base. It is a catalyst in the reaction. We do get it back. Recover it at the end, so it is a catalyst. We're using 2 equivalents of the benzaldehyde to 1 equivalent of the acetone. Our product, I'm going to go ahead and draw the product and then we'll go through the mechanism. So this is the Aldol condensation. Condensation, we are eliminating some small molecule to bring these together, to bring the aldehyde and the ketone together. And our product is a trans. Both of the double bonds are trans. Dibenzyl acetone. You have the possibility of forming trans or cis, but trans is more stable than the cis, so we will only get the trans. We are going to recrystallize the product, and so if there were to be any cis that is formed, it'd be a very small amount, and it will be removed by the recrystallization. Let's take a look at our mechanism for the reaction. Now, for our mechanism, let's take a look at the aldehyde and ketone. We've talked about in the lecture that if you're doing a crossed aldol, one must have alpha hydrogens and one must not. If we look at the benzaldehyde, this has no alpha hydrogen. Here is our alpha carbon, and there is no hydrogen on that carbon. If we look at the acetone, here is the alpha positions, and we do have alpha hydrogens, both of either one of those methyl groups. So our base, the first step of the mechanism, is our base is going to grab an alpha hydrogen. That grabs the alpha hydrogen off of the acetone. And that gives us the enolate anion. Now, that enolate anion is going to react with the benzaldehyde. That enolate will attack the carbonyl and kick the electrons up onto the oxygen. This will grab a hydrogen from water. Our hydroxide had grabbed the alpha hydrogen, that made water. We do have the water in there. That gives us the aldol addition product. And we've talked about in lecture that you must keep it cold to stop at the aldol addition product. By cold, I'm talking about 0 to 5 degrees. Anything warmer than that, and this will go ahead and go further, goes to the aldol condensation product. So even room temperature is enough to get this to go to the condensation. So we got our base back. We grab the hydrogen off the water, so we get the hydroxide back. That hydroxide is going to grab the alpha hydrogen. We've got 2 alpha positions, but the more acidic one is the alpha hydrogen that's in between the carbonyl and the OH. That additional oxygen pulling electrons inductively makes these more acidic than the methyl group. So we're going to grab an alpha hydrogen. Those electrons, let me just draw the hydrogen out here so we can see it. We're going to get that alpha hydrogen. The electrons in the carbon-hydrogen bond are going to kick toward the OH to form the double bond and kick the OH group off. Now there is our aldol condensation product. At least on this side we have done the condensation. Now we got our base back, and we had 2 equivalents of the benzaldehyde. If I had done 1 equivalent of benzaldehyde, 1 equivalent of benzaldehyde with 1 equivalent of acetone, we would stop here. Let me just write that. Stop here with 1 equivalent benzaldehyde and 1 equivalent acetone. But we had 2 to 1. We had 2 equivalents of benzaldehyde and 1 equivalent of acetone. So this will go ahead and react again. We're going to do the exact same reaction just on the other side. So that base is going to grab the alpha hydrogen. We'll leave the electrons there on the carbon. We make the enolate anion. That enolate anion will then react with the second equivalent of benzaldehyde. So we'll do the exact same thing as what we did just a moment ago. This will pick up the proton from the water. We had gotten our base back. So the base, this is our aldol addition product on that side. The base will go ahead and grab the alpha hydrogen that's in between the carbonyl and the OH. Those electrons kick toward the OH to form the double bond and kick the OH off, and that gives us the aldol condensation product on that side as well. So we're doing a double aldol condensation. And there is our final product. Again, we get the trans-trans. Both double bonds will be trans. If there were to be any cis that was formed, again, we are recrystallizing, and that will take care of any of the cis that might happen to form. the number of equivalents for this reaction is very, very important. As I mentioned, we're doing 2 equivalents of benzaldehyde and 1 equivalent of acetone. If you do one equivalent, I had the product there shown what we get. And so any slight change from 2 equivalents to 1 equivalent, you're going to get possible side products. If you've got more than 2 equivalents of benzaldehyde, then you just have extra benzaldehyde left in the reaction. So that's a possible contaminant. We just have extra that doesn't react. If you don't have exactly 1 equivalent of acetone, then there is problems. If you've got too much acetone, you're going to get some of that product that I've already erased off, where it was 1 equivalent. You'll have some of that as in your reaction. If you've got less than 1 equivalent of acetone, then that just means you've got an excess of benzaldehyde, so you've got that benzaldehyde as a contaminant. Now again, as I mentioned, we will get the trans-trans. Any cis-cis or a cis-trans that might form, that will be removed by the recrystallization. We could see that with the melting point if we still have any of that in there. We know the melting point of the trans-trans. Melting point of the trans-trans is 104 to 107. That's what I have written down. So if there was some cis-trans or a cis-cis, that would lower the melting point and broaden the range. So you will know if we have any of that present, but we shouldn't. The recrystallization should take care of that.